Yeah. I got an email. You're supposed to be filling out the survey on the teaching evaluation, and so the best way to do this is to do it now. So we'll take 5 minutes for you to fill out the survey, and then we'll start the lecture. I think it should be I think you should have gotten an email of where the survey is, as far as I understand. Does anybody recall getting an email about the teaching evaluation?
When were these supposed to get this?
I can check. Let me see. Yeah, so if you search your email for an email that says lecture evaluation, I think you should probably have an email. You don't have one? Okay. Let me see. So last semester people had a link, I think. Let me see. Okay, so yeah, I don't know. So my understanding is that you should have gotten an email. Okay, if not, we can try to. So you're positive you didn't get anything? Anybody? Okay, but there you did get an email.
Yeah, that was last semester.
Right.
Yeah, so it's probably more. Yeah.
Okay, so then let's see what's going on. Then we'll so you might get it then next week or so. Okay, so let's start with the lecture then, and I might ask you to fill out the evaluation next time. Okay. Yeah.
The starts for the exams when we.
Yeah, so we should check with our tutors to set up the poll. Yeah, so we'll do this also this week. Okay, great. So then we can start. Yeah, so this is just a recap from last week. So as I said, we were discussing graph neural networks. So we started with like a very simple graph where you just had like a bag of objects, no connections. And so this is basically just a set of objects without any relationships. And we developed like a neural network architecture that kind of respects the key symmetry of that type of data type, which is permutation invariance, right? So changing the order of the inputs should, if you have permutation equivariance, equally change the order of the outputs, which is kind of trivial given that you do like an element-wise computation. And then if you have a permutation invariant pooling operation, then and stick it through a neural network, you get a permutation invariant neural network, right? And so it's all about adapting the neural network architecture to match your data type. So convolutional neural networks has convolutions, local processing, and so yeah. That's a good point. Thank you. Very good. Yeah, so convolutional neural networks where basically, we had this idea of local processing, and then graph neural networks were some kind of generalization for that for systems where you do want to have like local message passing, but the objects are not arranged in the regular grid where you can figure out easily who the neighbors are, and so you use a graph structure to organize this message passing thing where you're basically doing what's called the graph convolution by preparing messages from the immediate neighborhood, where neighborhood is defined by the things that are you're connected to, right? And so we figured out like a number of ways to represent graphs and the data on graphs using matrices, which is very good because GPUs and so on, they're very good at matrix level processing. Okay, so then we want to go beyond space, right? And so in CNNs, we went from kind of this everyone reads from everyone, which we have in just feed forward, multi-layer perceptrons, right? You always connect every node to every other node in the next layer to kind of processing in the neighborhood. And so you kind of look both left and right. So in principle, you kind of want to process all of the data, but you process all of the data by kind of restricting this function to process only the neighboring data, right? And so this kind of the reason we did this is because in computer vision or visual processing in general, we have some kind of intuition that what happens in the left-hand corner of the image doesn't or shouldn't kind of materially influence how you process the lower left-hand corner. At some point, of course, you want to pool the information, which we did with max pooling, but kind of the core algorithms that should run like edge detection and texture detection and so on, they should be the same, right? The different corners might have different textures and different edges, but the algorithm to detect them should be the same, right? And yeah. Yes.
While it does give us permutation invariance, does it also destroy a lot of information because we turn essentially high-dimensional into.
It's still high dimensional, so you're not pooling into like a scalar value. So let's say you map like this phi neural network, maps it into like a 128 dimensional vector, and then you're averaging component-wise 128 dimensions. Then you still have 128 dimensions to represent the set, right? Like a good example of a deep set is like imagine like a histogram. Like a histogram is you have like many data instances and you put them into bins, right? And then if you have many objects, you fill the histograms like you have like a standard histogram, and like you basically capture the shape of the distribution of the objects, and that represents information about the entire set. It doesn't matter in a histogram how, like in what order do you fill the histogram. Like the information that you capture about the distribution of the object is always going to be the same. But there's like a non-negligible amount of information on how the objects as a set are distributed. Okay. So so we had spatial arrangements and local processing, and so now like graph neural networks kind of went off the deep end, and okay, we don't have any structure kind of from our intuition, and it's all given by a graph. But there's we can kind of take a different detour and say, okay, CNNs do spatial processing, and what is like temporal processing, right? So as physicists, you should appreciate that space and time are both important. And so now can we have like a special neural network that is tuned for time-like or temporal data, right? And so time-like data is ubiquitous as well. Like the convolution neural networks are very popular because there's a lot of visual processing we have to do in our lives. We also do a lot of kind of prediction in basically time-based processing. And so here are just a few examples. So in a sense, natural language, you can think of a time series. So it's like a sequence of words. So while I'm speaking to you, I'm giving a lecture, there's time is passing, and I'm every couple of seconds I'm saying some kind of word, right? And so you can think of text being a time series of words. There's also kind of more standard time series like data. So if you take like the function of temperature outside as a function of time, it's clearly kind of varying, or if you have larger time scales, you have like the different like winter, summer, spring, and so on. And there are some variations, and you might want to do like predictions based on that. Video data is basically you take images, which we already know how to process, but then you add a time dimension. And so time-like data is everywhere. And so it's makes sense to think about whether or not there's like a special architecture that kind of captures this. And this is, again, the entire name of the game in neural network architectures. We do have universal functional approximation in principle. We know in practice you would need an insane amount of data to really approximate every function. And so restricting the hypothesis set by exploiting some of the things that about the domain, which includes like the format of the data, is useful, right? And so this is what we call the inductive bias. And so now we're thinking about what is the inductive bias for time-like data. And so just as a kind of explanation how time-like data is often represented. And so the way that we capture time-like data is often by a sampling process. So something continues happening over time, but then we kind of take a snapshot of what is happening at a specific point in time every couple of seconds, for example, at like a specific, delta t. And then you basically get just like a series of data items. So if you have like images every second, then you have like a 2D grid, times however many seconds you observed. And so one of the main design choices you have to make when you're recording data is what is the time resolution of the data. So do you take a snapshot every day or every millisecond and so on? And you can also imagine like the way you process the data is somehow related to kind of your internal knowledge on how often you sample the data, right? What is the time resolution of the thing that you have? And so we'll get to this at the very end a bit, so maybe keep this in mind. And okay, so what are kind of typical tasks that we want, right? So we have all the typical tasks that we have in any case, and it's basic, for example, classification. So in the image domain, we had like MNIST, you have handwritten digits, 28 by 28 pixels. You want to predict, what kind of digit is in the image. And so it's the same thing, or you want to do like cat versus dog for photographs. And so, of course, you can also do classification on sequence-like data. And so, for example, one of the typical examples are reviews. If you like leave a review on Amazon or whatever, people are interested in rating this review. Is this a positive review? Is this a negative review? And so on. And so basically, you get a sequence of words. So then you have a classification whether or not that's a positive statement or a negative statement. And so here, like a well-trained classifier might say, okay, you have a positive sentence, and so this is trained on as typical on labeled data. So maybe somebody gave you like a bunch of sequences and like the human annotated version, whether or not they think it's a positive or a negative thing, and then the same way you have labeled image data, you have labeled sequences, and then you run classification on that. Okay, so then sometimes we also want to kind of generate something. So we will talk more about generative models, like generating new data kind of later on in the course, but you've all seen ChatGPT, I presume. And so this is basically what ChatGPT is doing, is trying to predict what is the next word given the words that you have, right? So it's not smart in, like a conventional way, but what ChatGPT is doing in the end is you write your prompt, right? And then it has like a possible number of words, and it's trying to figure out what is the most likely next word, right? And so your vocabulary might be English language vocabulary. There are various words in English language, like hello, physics, you, math, and so on. And so you can imagine there's a probability distribution of what like a possible plausible next word is, right? So the sentence probably is not going to say, like, based on the training data that you've seen, like the probability of the sentence being my favorite subject is you, it's probably not going to be the case, right? Or my favorite subject is what, even stranger. And the goal of machine learning model is basically to learn this conditional probability distribution, right? And then you randomly sample what the next word is, and then that gets presented to you in ChatGPT. Okay, there's also translation as a like a typical task. There's also like a generative task, but it's slightly different in the sense that you first encode or look at the full data to be translated, and then you translate the sentence. So for example, you have English to Georgian in this example, and then what's kind of interesting, so of course you might have 4 words in English might not correspond to like a 4-word sentence in Georgian, and so there's various things you need to think about. But this is also something where you have sequence-like data, so you translate step by step, and this is how the translated sentence gets generated. Okay, so we know very well how we process spatial data from convolutional neural networks. We have local data processing. You look left and right and so on. And so it's useful to think about like what is different about space or what's different about time in compared to space. And the main difference is that time has a direction, right? And so there's some notion of the past, the present, and the future. And so this is not something that you have necessarily in spatial data. So in spatial data, you have left and right, top and bottom, and so there are many dimensions, and there's not like one preferred dimension or direction, whereas in time, you have a very clear preferred direction. Time is running forwards, right? And so in particular, what's important is that, the future should not be able to influence the past, right? So there's some kind of logical constraint that we need to somehow implement in our neural networks. Okay, so then how can we maybe tune what we know about spatial processing to temporal processing? So we can basically say, okay, what we had in spatial processing is that we had, all right, let me just switch this off. Okay. So what you had in spatial processing, you're looking left and right. So your right-hand side was influencing you, it was giving you some information. The left-hand side was influencing you and was also giving you some information. And so basically what we had is, okay, when we were trying to compute, okay, what is the output of the convolution at a specific position, we had connections to the left and right. And so we are basically computing like a conditional function where the inputs are left and right, and then what we're trying to compute is the output, right? And so that's clearly not respecting the temporal constraints that we think are important in time-like data. And so what we can do is we can kind of very easily enforce a temporal direction by changing the way that we place the receptive field. So you can say, okay, if instead of this being kind of positions, these are times, and time is increasing from left to right, then, okay, if I'm trying to compute my current, some information about my current state, that might be influenced by kind of my current state that I already know, and maybe my past states that I had, at previous time steps. So my past can, of course, influence, some decisions that I make in the present, but the future should not be influencing, because I don't know what it is yet. And so this is basically a way to do it. So you just shift the receptive field, and so now, these future time steps don't, affect what is happening at this time step, right? It's a very simple change. And so with this, we can basically build convolutional neural networks, but that have this temporal constraint, right? Okay, so this is called the causal convolution. So it's the same idea. You have convolutional neural networks, but the way that you place the receptive field is changed in order to live with the constraints that we have with temporal data. And so this is what it looks like in a kind of convolutional neural network. As we said, so deep learning is all about stacking and composing multiple operations one by one. And in standard convolutional neural networks, we had multiple layers of convolution. They were always looking left and right, top and bottom, and collecting information from the immediate neighborhood. And so here you have basically convolutions, and what they're collecting basically not from the immediate neighborhood, but from the immediate past, right? So here you're collecting information from the last 4 time steps, kind of your short-term memory. And then by stacking these informations, you can expand the amount of past that you're exposed to, the same way that convolutional neural networks, after you do multiple passes of convolution, they acquire kind of more and more global information about the entire picture, because everybody's talking to their neighbors, and then if you talk to that neighbor, it will have information of its neighbors and so on. And with multiple rounds of convolution, you will kind of expand your field of view in a sense, right? And so in the temporal convolutions, basically you're expanding further, you can reach further down into the past if you stack multiple layers of temporal convolution. So the disadvantage of this strategy is that, okay, if you want to really kind of have long-term memory and be able to affect your current decision at the current time step by something that happened a very long time ago, then you need to have a very, very deep composition of temporal convolution to be able to reach it effectively, right? And so this is a slight disadvantage with causal convolutions. Okay, like a possible solution that is also used actually in spatial processing is what's called the dilated convolution. So instead of collecting, everything around your immediate neighborhood, what you can do is you can kind of selectively say, how densely do you sample your neighborhood, and without increasing the amount of processing you need to do. And one way to do it is to kind of look at every other step. And so this is called the dilated convolution, where you're saying, okay, I'm capturing kind of what's happening in this neighborhood by kind of coarsely sampling the neighborhood, and then I have computation left to reach further into my the wider neighborhood, and using this dilated convolution. And so the same is something you can do with temporal convolutions. You can do a dilated convolution where you maybe sometimes you exponentially increase the receptive field of depth, basically by using these dilated convolutions multiple times, right? Okay, but still, I mean, it's still like doesn't solve the problem at its core. It's still, if you have like a finite number of forward convolutions, there's only like a finite amount of time that you can reach back into your history to make some kind of decision, right? It will not have any type of true long-term memory. Okay, here's an example of these temporal dilated convolutions at work. So this is a neural network to analyze like real-time speech waveforms. And so you can see there's structure both at the local level that is important, and there's very large long-range structure when you zoom out a lot. And so it's not enough to just do local processing. You want to have a global view. And so it's important to be able to reach far back to kind of capture this global structure. And so the dilated convolution were a way to do this. And so this is a neural network architecture that was designed by Google and was called WaveNet at the time, right? And so you can see how this dilated convolution is working. All right, so now the question that maybe you're asking, okay, is there a solution to this problem? So can we somehow have very, very long-term memory where we, somehow keep in mind what has happened a long time ago, and that it's not limited by some finite number of operations? And then you can think about, how do you do this in real life? We do have long-range memory, so you think at least think that you remember something about your early childhood and so on. And so you're very selective, I mean, in like a finite capacity brain, right? So you're maybe selective in what you're remembering at every point in time, but it's not like you have some amnesia cutoff that you only remember the last 5 years, right? I hope, at least. And so, we have some kind of notion of memories, and it's not only humans that have this, computers also have this. So the entire architecture of computers is built around, you have like a processing unit, which is finite in size. There is some kind of memory, and, you have files on your hard drive that are maybe 10 years old. There are files that are, like a millisecond old, like your cache in your browser, your cookies and whatever. And so, but the computer is deciding which things should be deleted, which things should be kept around for a long time. And so this type of, it all happens in like a finite amount of resources, right? It doesn't mean that just because you have, possibly long range, source of data that you need to have like an equivalent size of memory, because there's no need to remember everything, but you might want to remember the relevant things, right? And so the question is, can we somehow implement this notion of memory inside of a neural network? Okay, so yes, we can. And so the way that we want to basically do it is, so what we want to do is we want to have a function where kind of the output is a function of like the current time step and the past, right? And so that past should like possibly range like infinitely back into the past. And so the way that we do it is that we say, okay, instead of keeping track of every, like the full fidelity data, all of the bits of information that ever happened in the past, which might be a lot, what we can do is we can compress it into, like a finite size things, which we will call memory or hidden state H, right? And then we basically say, okay, this H vector basically represents everything that happened until the last time step. So somehow we've managed a way to encode all of the previous history, or like the relevant pieces of the previous history, in like a finite size vector H t minus 1. And so we are basically saying, okay, our function to predict the next time step or compute something about the next time step is going to be a function that happens, is affected by the current input, your present and the past, but the past is encoded in like a finite size thing, which is this H. Okay. And so that works. So then additionally, what we need to know, we need to somehow say, okay, when something important happens, okay, you have some kind of memory, and something important happens in your life, you kind of update your memory. You kind of make sure that this is something you remember, maybe because you think it's going to be important for the future. And so it's not just enough to kind of be able to output things based on the full past and like the present input. You also need a way to, update the memory given some new type of information, right? So let's say you get some new type of information. You want to somehow, maybe throw something that is slightly marginally less relevant to your life. You want to throw it out of your memory, and you use the same space to, store this new thing. So if you have on your phone, you want to take some new picture because something interesting is happening, you delete some old pictures to make space for the new pictures, right? And and then you're selective with like which pictures you're deleting. So that's some kind of algorithm that happens that figures out what the new memory, the updated memory should look like. And so really what we want to have a function that kind of eats the current input, like your present information, together with the past. And what it outputs is some kind of output, okay, you're reacting to the input in the present, and it should also update the internal state, your memory, based taking into account what you just, what type of information you just consumed, right? So you have this kind of function has two inputs. It takes in data and memory, and it outputs data again and memory, right? And so this is the type of function that we want to, model with the neural network. Okay, so and this is what brings us to recurrent neural networks, or sometimes they're also called RNNs. And so the recurrent neural network receives two inputs. And so most of the neural networks we discuss now, I mean, they receive kind of one input, like data, like the image and so on, and you just do one computation. And here you receive two inputs. You have the current data at your current time step, what maybe like what you're seeing right now with your eyes, and you get the memory, up to that point. And then the job of the neural network is to process the new data in the context of the memory, and then output some kind of value, and also output some updated memory. And so this is what it looks like, right? So we get the current, like the view of the past plus the current information that we have at the current time step, and then we output some kind of, result. So maybe you're kind of classifying what you're seeing right now, and then you're also updating your memory, what, you know, with the information, what you've just seen, right? And so this is kind of the basic structure. And then why is it called recurrent neural network? Is because we can basically do this kind of over and over again. And, you know, this is basically what it means to kind of recurrently process information. And this is exactly how a computer works. Like a computer gets you, like as an input, gets its keystroke, it gets its current memory based on the keystroke, and the memory does something. Maybe it displays something. So this is the output, but it also updated the internal memory. Then you do the next keystroke. So there's some new input. You get the memory at that time point. Maybe it displays something, which is the output. And like a computer just works like this. And this is what's called the von Neumann architecture of computers. And you as a human likely also kind of work this way. Okay, so you have your kind of current memory, which is in your brain somewhere. You know, you have some sensory input, and based on, you know, your state of mind and the sensory input that you get, you have some kind of action. So there's some kind of output, and then you just repeat this, you know, many times. And this is always the same neural network. So just because you need to process a very long range sequence doesn't mean your computer needs to become bigger and bigger and bigger and bigger. You just need to have like a good, well-trained system to you know, process information. You know, your brain doesn't get bigger just because you live longer, right? Okay, so, and then this is kind of the basic structure of a neural network. And sometimes we also kind of represent it in this way, because basically the output, you know, the updated memory is going to be the input memory at the next time step. And so there's this recurrent structure where basically information flows kind of in this recurrent fashion. Okay. So then there are various ways that we can build such a recurrent cell. And so we can basically start from a, so because you need to produce two things. You need to produce the updated memory, and then you need to produce the output. And so in which order you do this is, you know, sometimes, I mean, it's not specified. So, okay, we can think of like what a good way to do it. So like a natural way to do it is to first, okay, consume the sensory input. So like the new data, and so to update the memory based on that. So you update, you know, you kind of incorporate new information into your memory. And so the first thing that you do is you have like an updating function that takes the data, it takes the past memory, and then it updates kind of to a new memory. And so then it looks something like this. And then, so what kind of, so how could we model this function? So you're like in a deep learning course. And so the way to model this function is that we model this function with a neural network. And so the simplest neural network that we can write is perceptron, right? And so this is exactly what a perceptron is. You have, you know, your matrix multiplication with the input plus a bias vector, and now it's all wrapped in, you know, nonlinearity, right? So this is, you know, some kind of family of functions. It's trainable. They're like, you know, how exactly information is processed depends on the details of the weights and the bias. But you know, it's a flexible kind of strategy to process information. So we'll maybe use this perceptron for our memory updating function. Okay, but the principle could be any like gigantic neural network, but this is the simplest that we can come up with. Okay, so then you know, if we basically take the view that the main component that, you know, holds all of the information about the data is the memory, we can kind of assume that, okay, now we're asked to produce an output. So you incorporated the information, and now like what do we display on the display, or like what action do you take? Do you go left or do you take right? You know, what kind of reaction do you have based on what you've just seen? And so the way that it goes is basically that you okay, you incorporated the new information into your memory, and now you're querying your memory. Okay, what should I do? And so this is kind of like a readout function. And so we want to have a function that takes in the memory and then it produces an output, right? And so what should this readout function be? I don't know, like we don't know what the best way is to process the memory. So the best way to do it is to just model it as a neural network. So there's going to be some kind of strategy to produce an output based on the current state of the memory. And what exactly it is, we don't know, but we know that we'll just model it as a perceptron and hopefully, that is flexible enough to give you, the right expressivity to learn the right strategy. So you want to learn how to incorporate, so the neural network here is basically learning how to incorporate, new information into memory. So basically learns, what is important, so what should I keep in mind, what types of input should I ignore, how should I update my memory based on the data. And here it's basically, okay, how should I produce an output based on my current state of the memory. And so this is a kind of very frequently appearing strategy. So you kind of think about like, what is a good strategy to organize the computation, right? And then you leave the details to the neural network to be learned from data, right? It's with convolutional neural networks was exactly the same idea. So we kind of had this idea that local processing is useful. So we arranged for like filters to move over the data and, not look at everything, but like what exactly the filter should be like, is it edge detection important, or is like texture detection important, and so on. We didn't specify. So we just had like a parameterized, we like built the general scaffolding on how to do the computation, and then the details are left to the machine to figure out itself. And so it's the same idea with recurrent neural networks. We prescribed there should be some method to incorporate new information. There should be a method to extract information from the memory, but how we do this is something we leave to be learned from data. Okay, so then we can put these things together, and so this is what's called, like, it's the simplest type of a recurrent neural network. It's called the Elman network. So basically you have your new information, you have your past view of the memory, you update your memory using our memory update function, which is parameterized and should be learned. And then we get our new memory. And so this is something that we need to output anyways, our updated memory. But then based on this new memory, we project or we extract information in order to produce an output, right? Okay, so this is recurrent neural network. It's a simple one, so might not be the most powerful one, but it's like the most straightforward way to implement something like this. Okay, so what's important, so already something we discussed. It's basically the strategy, so the learned strategy on how to incorporate new information, how to extract information. So this is just like a general skill that you learn once, and so this is something that you apply at every time step. So your judgment, what is important information that I should be writing into memory, this is not something that changes over time. What's changing over time is what type of information you're receiving and what your current state of memory is. But the general strategy to incorporate information is you learn once. And so it's the same in a CNN where we learned the important filters once and then we apply them to every image, right? And so it's kind of the same idea. And what this gives you is this parameter efficient. So in a CNN, like the only place where you pay for parameters is like the size of the filter. Like the neural network doesn't scale with the size of the image. And here it's the same idea. The RNN doesn't scale, like the complexity of the RNN, how many parameters there are, doesn't scale with the length of the time sequence that you have, but you just have you know what you do at every time step, and then you just do it many times in a row, right? So then the same way that CNNs can process arbitrarily large images, RNNs can process arbitrarily long sequences. Okay, so then what is the role of the memory? So it's just like some n numbers. So typically you have like some kind of memory vector, which is maybe 128 long vector, and so you just have allocate some fixed amount of space to hold like a view of the past, but it necessarily needs to be compressed because you can't just remember everything. You only have finite amount of space, and so we basically need to learn how to filter the data and how to judge whether or not it's something that should end up in memory or should be ignored. And the same data might be judged important depending on the context of the memory, right? So that's why this memory update function is not only a function of the data, but it's also a function of the current state of the memory. All right. So this is an analogy. As I said, I mean, computers clearly have types of memory, right? And so we can very clearly see that this is kind of like a neural version of a computer, right? So if you have like a computer code, you could imagine something like this, where you have like a computer code that processes a sequence of characters, right? And then so we have some kind of memory. So we don't want to keep track of every character that is shown to us at all. So maybe like the only thing that we care about is like what is the last vowel that we've seen, and how many vowels have we seen in total, right? So we don't need a lot of memory, so we can process like an arbitrarily long sequence of data, and stuff that we want to remember about the sequence is not going to change just because the sequence gets longer. And so like a typical result that or implementation that you might have is, okay, you have some kind of sequence, and then you basically say, okay, if the next character in the sequence is a vowel, then you increase your memory location that represents the vowel count by 1, and then you also update the memory to see what the last vowel is, and then maybe the output, so the reaction of getting like a new input is taking kind of the last vowel and outputting like an uppercase version of this, right? So this is a very simple program that you might think you're interested in. And so in order to produce the output, what's important, you need to access the memory in order to produce the output. And so you first need to update the memory, and then based on the memory, you're producing your output. And so this is what this looks like if you run this program on a sequence. So you have AESTOWI, right? And so it's always, the output should be the last vowel that has been seen in uppercase. And so here, like the last vowel is going to be A, right? This first one. So we output capital A. Then we have E. So it's a vowel. So we need to update our memory, and then we need to capitalize it. And then we get like a few non-vowels, so S and T, and so the output should still be capital E and capital E. At that point, we see a new vowel, and so we need to update our memory, and then we produce a capitalized version of that. Right, so it's a very simple program that runs. It eats a sequence, it produces another sequence of the same length, and it has some kind of memory at the very end. So once we run it, okay, the last vowel is going to be I, and the total number of vowels that we've seen is 4. Okay, and so the way that this looks like kind of internally, if you unroll, okay, what does the memory look like at every point in time, is that, you're counting the vowels, and then you have like what the last vowel is, and based on that you produce your output. Okay, and so basically recurrent neural network has exactly the same structure. To see this, you can kind of rewrite this process sequence as kind of like a program like this. So it's exactly the same program, but you basically have like a memory updating function which takes the memory and the new data item, right? And so what we do in this case, our learn strategy in order to solve our task is to recognize whether or not it's an important piece of information. So is the thing a vowel? If yes, we'll kind of add our count, and then we'll update what the last vowel is. And so we update the memory, and we get a new memory. And then if we want to produce the output, we kind of process the memory at that point. And then we access the last vowel and then capitalize it, right? And so this structure is exactly what a recurrent neural network is, except that these update memory, instead of being code, these are learnable functions that we will learn based on data. What the right strategy is going to be to solve whatever task you want. Maybe your task is, instead of doing like the simplistic thing, maybe it's translating sentences and so on. And so there, it's not so clear what the right strategy should be, and this is what you can learn from the data. Okay, so basically, RNNs are kind of loopy programs with learned and differentiable update and information extraction functions, right? And they're all operating on some fixed memory and like a possibly infinite stream of inputs. Okay, so here's a blog post that I absolutely recommend you should be reading. So maybe this is something you can do over the weekend or something like this. And so this very simple structure is, I mean, in the early days of the neural networks, was kind of recognized to be very, very powerful. And so it's kind of the precursors of ChatGPT, and it was a little bit surprising. And so in physics, we sometimes speak about the unreasonable effectiveness of mathematics in describing nature, right? So it's not clear why like math should be the language in which we can describe a lot of things that we see in the world. And so here it's kind of the same idea. It's like somehow recurrent neural networks are unreasonably effective at very kind of tasks that seem very complicated. But basically because it's kind of like a neural version of a computer, and we know like a computer can do if it has like the right program, it can do basically anything. This is something that you see in fairly complicated tasks with fairly simple recurrent neural networks. So I'll encourage you to read this. Here are just a few examples of what is happening inside of a recurrent neural network when you're processing data. So you can look into what is happening to the memory. And so here, you can recognize that there are certain positions in the memory that keep track on whether or not you're at the beginning or the end of a line in a text. And so this is not a strategy that is put into the neural network, but you can see, okay, there's a cell, so like a memory location, that is tracking whether or not, so here you're at the beginning of the line, and then you're approaching the end of the line, and then you see a line break. And then and so on. And so based on, you might think, so there, like a variable number of characters, but it learned kind of to keep in track, okay, like on average, after like 50, 60 characters, I'm probably approaching the end of the line. And so there's like a learned strategy that, kind of senses whether or not you're close to the end of a line in text. There are specific memory locations that keep track in its state whether or not you are inside of quotes or not, right? So this is important if you want to do like speech modeling and so on. It basically figures out, okay, here like a quoted section begins, and this memory has like a specific value until you see kind of the right signal to stop that's a section, which is like the quotation mark again. And then, that memory location has like a different value. It's as if you had somewhere to ask, am I in a, quoted section in the text or not, right? And it's also not something that you trained the neural network to do kind of by hand, but it's some like a behavior that the neural network discovered on its own, right? So who has used language models for coding? Have you used ChatGPT to generate Python code? Yeah. So, I mean, to understand code, it's important to know whether or not you're like in an if statement and things like this. And so you can see it's kind of like a generalized version of this quotation thing. So it knows whether or not you're inside of an if statement. And so you can see while the neural network is processing the input data, you can see what it is doing. And so it's very similar to convolutional neural networks where some of the filters that were learned were very interpretable, and we knew that they're basically sensitive to edges or to curves or so on. But there, of course, like with the filters in convolutional neural networks, some things that are completely, uninterpretable. And so, while this is very suggestive, there's a lot of stuff that maybe is not so clear what the neural network is doing, but it's kind of interesting to see. And then with like a simple neural network like this, you can generate text that sounds like Shakespeare and so on, like within 10 minutes on your laptop without any problem. Okay, so then, we still want to stack. So there's like a sense that we are processing a sequence, right? And then we are producing a sequence, right? So in some ways, it's like what a recurrent neural network does is like takes an input sequence and it produces an output sequence, right? By passing in the memory on like the vertical, on the horizontal axis. But kind of if you think of it as a kind of sequence to sequence transform, it's like a shallow transformation. There's like one step of generating outputs. And so we know that deep learning thrives on composition and on deep composition. And so we just use the same trick that we use in convolutions, the same trick that we use in graph neural networks. We're just going to stack this thing, and we hope that we'll learn the right strategy and be able to represent data in a useful way, so that if so that we increase the expressivity and how much information we can extract from this sequence. And so this is then basically like the deep network version of a recurrent neural network. And so we've done the same thing for MLPs. We've done the same things for CNNs, for GNNs. And so now we're going to do the same thing for recurrent neural networks as well. Okay, so we have the same idea as always. So the deep learning philosophy is we have like a learned feature extraction instead of having humans, figure out what the important features are in like some data item. We basically take the raw low-level data and we just pass it through like a learnable feature extraction. Then hopefully we prepare the data in a way that makes the final task easy. And so we have the feature extraction phase, and then the head of the neural network is just kind of solving some kind of simple problem. And so here it's a deep MLP. Here we had the CNN. The feature extraction was through convolutions. In GNNs, we had feature extraction through graph convolutions, and then we always follow this up with like a simple projection that is maybe like a small MLP that does kind of the final post-processing. And so with RNNs, we're going to do the same thing. So let's see how we can do this with RNNs. And so we had multiple patterns already in graph neural networks, depending on the tasks that we wanted to do. So sometimes in graph neural networks, we wanted to do like a node level classification. So you do some rounds of communication, then you want to maybe do like a node level classification. Is this person above a certain age? Yes or no? Or is this person like a good basketball player? Like, if all your friends are 2 meters 20, maybe that implies you are a good basketball player or something like this. And so you want to do like a node level classification, right? And so it's we can do the same thing. We can do like a word level classification based on context. So we could do like so basically the RNN is mixing the words, the information that is like in the neighboring words. And then we can do like a word level classification. So many to many. We can also do kind of like a sequence-wide task. And so then the GNN case, we're pooling everything in a permutation invariant way. And then we have a neural network that does the final processing. Here, the RNN is not permutation invariance because there was a certain order in which you put in the information, and clearly, the order matters. Whether you say like I like you or you like me is like a different meaning, and so the order matters. And basically the strategy is so time goes in the right direction, and so this rightmost object after all the deep stacks of RNN, it will have seen the entire sequence. So this is the only node that knows about the entire, or like the rightmost column is the only column that knows about the entire sequence. And so basically the strategy could be to attach a neural network to process the final output to do like a sequence-wide classification. For example, if you have a review, it's like a bunch of words like strung together. And so if you want to judge whether or not the review is any good, is it a positive review or a negative review, you would look at the last time step and see what information is captured there. There are kind of some details because recurrent neural networks has two different outputs. So it always outputs like the memory, and it outputs the output projection. So you can either kind of do the final classification on the final output of the final layer of the recurrent neural network, or you can look at the memory, like what was stored in the memory, and then inspect the memory to do the final prediction. So you've seen the entire review. Okay, what do you think about the review based on what you have in memory after you've seen all the words? All right. So long sequences are tricky. So I mean, in principle, RNNs can deal with arbitrary long sequences. So in a sense, it's just a another type of deep neural networks where basically the weights of every layer are the same, right? Because you're always kind of processing the same like the information in the same way. And so if you think of it as a neural network that is deep in time, then having sequences that are like 100 tokens long or 1,000 tokens long is not crazy to think about. Okay, like if you're trying to analyze tweets, it's like 280 words, maybe it's like 1,000 characters. And so you need to, or that's like tweet, I guess it's like 280 characters. And so it's not crazy that you have like fairly long sequences. And so to be able to handle long sequences is an important, objective. But we know that deep networks can become unstable with high depth, right? And so we did all of this preconditioning of the weight matrices with Xavier initialization and so on to keep all of the gradients under control. And so we need to think about how we can initialize a neural network in an efficient way so that this deep processing works, right? And so for deep MLPs, the way that we did this is we had kind of like we had two strategies, right? So we had kind of initialization tricks to just kind of initialize the neural network in a way that the gradients are stable and the outputs are stable. And then we also had this idea of skip connections where you're basically nesting the functions. And so you learn like a small correction on the output every time. And so this opened up two ways for information to flow. You have like the information flow through the residual connection, through the kind of residual correction piece. And then you have like a skip connection, like a highway connection that gives you direct access to what happened in the past. And so this is a shortcut. And so this way you don't forget so easily what was before, right? Because you don't need to go through this additional piece. And so both of these ideas apply to recurrent neural networks as well. And so to see, how we do this, so we're going to talk about gating. And so let's forget about neural networks for a bit. And we just are going to do like some numerics. And so let's look at a kind of length 4 array. So we have an array, NumPy 1, 2, 3, 4, right? Okay. So let's see what we do with this. So we can basically, so our job is now to extract information from this array. And for example, you might have the task extract all of the even numbers or extract all of the numbers smaller than 2. And the way that you can do it is by multiplying the array by a binary mask, right? So you can basically say, okay, if I multiply the positions where like the uneven numbers are 0, then the only information I retain are the even numbers, right? And so we can extract all the even numbers in this way. We can extract all the numbers smaller than 2 by looking at every number in this array, judging whether or not it's smaller than 2. And if yes, then we'll kind of add a 1 in the mask. If not, we'll add a 0 in the mask. Does that make sense? Okay, great. So so the important thing is by multiplying with a binary mask, you can extract kind of information in a targeted way from a potentially large data source. And now we can also insert information in the block of memory by the same kind of strategy. So for example, imagine our task is we want to replace all of the even numbers by squares. And so we have our array 1, 2, 3, 4. So what we can do is we can just compare the squares for all the numbers. Okay, we're doing some superfluous computation, but maybe we don't care. So let's just compute all the squares. So it's like 1, 4, 9, 16. Imagine we don't know which one is even. And so we'll just compute the squares for everything. But now we can say, okay, but I only want to replace the even numbers. And the way to do it is to apply or like figure out the mask, where are the even numbers? And then, the point where the even numbers is, you kind of take the data from B. And for all the places where it's not an even number, you take the original values A, right? Does that make sense? So, okay, 1 minus even mask is 1, 0, 1, 0. And so you basically multiply A with 1, 0, 1, 0. So you get 1 and 3 from this piece, right? And then you interleave this with a B, but a B is multiplied by this mask. And so then the output that you get is like 1, 4, 3, 16. So the even numbers you squared and the uneven numbers you left untouched. Does that make sense? Yeah? Okay. So basically, this is a way, kind of like a little bit convoluted way to manipulate memory by masking things one way or the other. And what we've achieved is kind of like a targeted overwrite of the memory. So here we didn't touch the first and the third position, but we did touch the second and fourth position and did something very specific to those memory locations. Okay. So then yeah, so you can insert new information, and then we can have our updated thing. So we can also do like add the square to all the even numbers, and so you can see some other example as well. Okay, so now the problem is, so that seems like a useful way to manipulate memory. So it's works on arrays, and we know array-based programming is useful, but the problem is binary masks are not differentiable, right? And so we know that in order to do gradient-based optimization of a neural network and to optimize the neural network, we need to have differentiable things. And so if we start kind of doing like hard masks like this, so flipping from 0 to 1 here is like, it's not something that is differentiable, and it's not useful for neural network training. But we want to learn something similar, right? So we want to update our memory vector in a way, based on the new information. So somehow, okay, what is, like a soft version of a binary mask? And so the way that we are going to do this is we use the same trick that we had already with multi-layer perceptron. So there we had the same problem with our perceptron, not the multi-layer perceptron. Just the perceptron, we had like a hard jump in output. So it went from 0 all the way, and then suddenly it jumped to 1. And then our strategy is to soften this with a sigmoid, right? And so generally it has like the same behavior, but it has like a soft transition from 0 to 1. And so that enabled gradients to flow, and then we can do gradient-based optimization. And so we're going to use the same trick by, for our memory updating functions. And so, okay, so basically what we can do is we can say, okay, we want our neural network to basically produce like a mask on, where to read the memory or where to write the memory. And so if the neural network tells us, okay, at this position, there's like a high number, it means, okay, here we want to update this position a lot. If it's a low number, we want to kind of update this position less. And here again more, and here this position we don't want to update maybe at all. And so there's like a kind of smooth version of what it means to access a specific memory location. And so here again we have like the hard version of this mask. So if you would threshold this, maybe at 0.5, you would get like this hard version of a mask, which is what we had before. But now we just have the soft version of this mask, and we're going to use the soft version, but then do the same types of operation that we've seen before. Okay, so then what does it mean to update the memory? We basically have our memory mask, which is some soft mask like this, and with our input mask, so we kind of know where do we want to write things, where do we want to read things, and then we compute some new values, maybe with some kind of function. And then the way that we're going to update our memory is basically say, okay, we're going to mask out the previous memory, and then add like the new values on top of this, right? And so it's the same, just as a reminder, the same way that we had here. So we have A and B. So our original data, we have our squared data. So there's our new values that we maybe want to put into our memory. And then we have our input mask, which is, okay, I want to read in all of the data. And then for my new values, I only want to update like specific points, and then I get my memory manipulation. And so here, like this is all done with hard mask, and you can try what the output is with soft mask, and it's basically going to be very similar. Okay, so then you can as students of the TUM, you can be very proud because the best known gated RNN was invented here at TUM. So this is Jürgen Schmidhuber, who is a very famous, one of the kind of pioneers of deep learning. And this is Sepp Hochleiter. He is his PhD student or maybe diploma student, I don't know. And so you can see, okay, this is from 1997. And there they introduced basically, this idea of a gated RNN. And so the idea is that with these gates, you can control how the memory gets manipulated. So you can, say, okay, this piece of information is important. I want to update the memory. Or if you don't want to update the memory, the gate is just going to say 0, 0, 0, 0 everywhere, and you're just not going to touch the memory at all, right? And so what the LSTM does is basically it splits the memory into like a long-term cell that is protected by gates, and then you have like a short-term hidden state, which is kind of like the short-term memory that you have, and then you are very judicious in deciding when you want to put information into this long-term cell at all, right? And so the idea is that with this you can, so it's kind of like a skip connection in the sense that you want to protect the memory from being overwritten all of the time, and that helps you keep information from a long time ago in the memory and keep it fresh so that it's still available when you need it. Okay, so what the LSTM does, it basically first computes a forget gate. So basically it tells me, okay, so you always want to make these decisions based on the new input data and the current state of the memory. So these neural networks always take both the current data and the memory, and then you basically decide what to keep and what to forget, right? And so you want to decide based on the short-term memory and the new data, what you want to update in the long-term memory. And so if this neural network says kind of roughly like gives you a high value close to 1, basically means you want to keep it. If it gives you like a value close to 0, it's that means that you want to forget that particular whatever information is at this location in the memory vector. Okay, so then there's another type of neural network. So you need to compute possible new cell values. So what we had like 1, 2, 3, 4. We just computed all of the squares of the numbers. So we want to somehow compute based on the new information and the information of the memory, what are like possible things we want to write into the memory at every location. And so this is also just modeled again as a simple neural network. And so here, the story is, okay, deciding, based on the short-term memory and the new data, what of the new data is, or what type of data is worth storing into memory. Okay, and then there's some more neural networks. So you have what's called an insert gate. And so you basically have, again, a neural network that takes in the data, takes in the memory, and basically it computes the new values based on the state. Basically gives you like a gate on, where you want to insert values and where you want to not insert values into the memory. Okay, so then how do we update the cell in the controlled way? We basically say, okay, we have our forget gate. And so the things where, our forget gate is high, it means we want to keep the data. We don't want to forget it. If the forget gate says 0, it says, okay, this piece of the kind of previous memory you want to forget. And this is the same. So this strategy is the same strategy as what we had here, right? So this strategy, so you have your gate, you multiply kind of the current state of the memory with the gate, and then you add like the new information with kind of like the opposite gate, right? And then you add both of these things together. And so we do the same thing now here. So we multiply the past state with our forget gate, and when we multiply the new state with our input gate, and then we add both of these together, and this is going to be our new memory. Okay, so then now the only thing that we need to figure out, okay, we updated our memory. Now we need to figure out how do we extract information again from our memory. And again, it's going to be like a neural network that gives us a gate, like which memory locations do we want to read out of our memory. And so that's just going to give us a mask again. And so based on the data and the short-term memory, we have like a gate that tells us how to extract information from our long-term memory like this. So we have our long-term memory, we multiply it with a mask, and this is going to be our new short-term memory from which we generate our new output. Okay, so this is slightly complicated. So there are much simpler versions of a recurrent neural network, as you've seen, where it's just like simple neural networks. But here, like this gated version is very powerful in kind of protecting the memory and not overriding it all the time. And so here you see like a small, graphic that does this. So basically, you have like a bunch of neural networks that compute these masks, which memory locations to access or modify. And then you have a neural network that produces candidate values, and then how you update your new hidden state. Okay, so there are other options. So for example, there's the GRU unit, like a general recurrent unit, which is a much simpler architecture. But LSTM is kind of like the original architecture that was able to perform very well across very long amounts of time. All right, so how do we do this in PyTorch? As always, with convolutions and with graph neural networks and so on, you don't need to think about a lot of these details once you've understood them. But in PyTorch, you can basically just say, okay, I want to have a recurrent neural networks. The input data is going to be 10-dimensional. My memory size is going to be 20-dimensional. And then I want to stack multiple layers of, sequence to sequence processing. And then you put in, for example, like 100 examples of, sequences that are 7 items long, but, at every item you have a 10-dimensional thing, right? So for example, you have, maybe some kind of encoded version of a word, which is 10-dimensional. And then you can put this into your RNN, and the output is going to be just the same thing, but just you have the hidden state is 20-dimensional, and so you convert it like a sequence with 7 items with 10-dimensional pieces at every position into 7 items with 20-dimensional pieces at every input. Okay, so then you can also access. So if you use this is a simple RNN. If you use an LSTM, you can access both the short-term memory and the long-term memory. And so you can look a little bit into the documentation, but basically the upshot is with like a few lines of code, you can do a lot of this complicated gating and so on. You don't need to think about it. It's just done for you internally. All right, so then maybe I wanted to, before we close, kind of connect this to symmetry. So the last couple of lectures, I was highlighting the fact that the kind of the neural network architecture has a lot to do with symmetry. So in convolutional neural networks, the symmetry was translation equivariance and translation invariance. In graph neural networks, it was permutation invariance and permutation equivariance. And kind of interesting to think about what is the symmetry that is underlying LSTMs or like recurrent neural networks. And basically it touches back on the thing that I had at the very beginning. So somehow the strategy, like your strategy on how aggressively you want to update your memory depends on the knowledge how densely you sample the data. So if you know that your sample data is, you get samples every 100 milliseconds, your strategy on how to update your memory might be different than if you just get data every hour, right? So if you want to somehow do like a weather prediction and you know that your data is only sampled every hour, you want to basically completely erase your memory and completely update it with the current state, right? Because clearly like the past has no relation anymore to the present. And so there's some kind of symmetry that is related to, okay, if you were to change like a scale change in like the sampling frequency should basically result in an equivalent change in how you update the neural network to handle this type of new sampling density. And so this is a little bit beyond the lecture, but I wanted to mention it here because kind of it means that this doesn't break the general picture that neural networks are, or architecture, very deeply connected to symmetry. So if you have time, I encourage you to look at this lecture, on YouTube, and so this might, make this connection stronger about symmetries and recurrent neural networks. Okay, so with this, I think we can close for today. We're going to talk a little bit how to train neural networks, recurrent neural networks in the next lecture, and then we're moving on to transformers and things like this, which are the architecture that underlie GPT. And so I should say, at the very beginning, one of the early or easy examples of a time sequence is natural language, like a sequence of words. And so recurrent neural networks were the main architecture for natural language processing for many, many times. But then like a similar idea to this gating then led to transformers, which completely replaced recurrent neural networks and natural language processing. And so in a way, the RNNs are a little bit out of vogue. They might be coming back in a slightly different way, but it's important to know for historical context what the idea behind this architecture is. All right, thank you.